Okay, I'm going to be working out 3.5. This section is what are we doing here? 3.5 inverse trig functions. Now, this video is going to be done using my tablet because I don't have access to a video camera at the moment, and I have a little bit of time to get this done. So here we go. The first problem that I'm going to be working on is number 1. So number 1 has parts A and B. So part A is asking us to figure out what sine inverse of root 3 over 2 is. So what we need to do this is to have a knowledge of the unit circle. So our unit circle has some pretty common angles on it that we have to be familiar with. And so what this is really asking us is sine of what angle equals root 3 over 2. And in addition to that, because we are looking at the inverse trig function, we should realize that from pre-cal, the inverse trig function, what is happening here? The inverse trig function is only defined between negative pi over 2 and pi over 2. That's the domain of the inverse, or I should say that is the range of the inverse trig function. It's only going to spit out answers between negative pi over 2 and pi over 2. So we can only look at angles that go this way, negative over to negative pi over 2, and this way, positive pi over 2. And also, because it's a sine, or arc sine, when we say sine of what angle is root 3 over 2, this corresponds to the y coordinate. So what this is really saying is where on the unit circle, over here on the unit circle, is our y coordinate root 3 over 2, and this is where you need to know the unit circle. So you should know that at 60 degrees, the coordinates of that point are 1/2 and root 3 over 2. And we wanted to know where that y coordinate was root 3 over 2, and that's where it happens. So this angle here that we have is the angle 60 degrees, or in radians, pi over 3. So the answer to this question is, I'm going to do it in radians, pi over 3. So it's very important for us to remember that even though over here in the second quadrant we also have a point that has the same y coordinate, because of the restrictions on the inverse trig function, we are not allowed to look over there. So that's why we get only one output, and that is an important characteristic of being able to define the inverse trig function as a function. Okay, moving on. Part B is asking for cosine inverse of -1. So this is the same thing. It's wanting us to know about the unit circle. This is really saying where is cosine, right? Or sorry, cosine of what angle is equal to -1. And the cosine is the x coordinate. So we're going to be looking on the unit circle, and we are dealing with the inverse cosine function, which means that we are only allowed to look between 0 and pi. So the range of this is the things that come out are angles between 0 and pi. So we're only allowed to look here in the first and the second quadrant. And so it's pretty obvious that the only place that the x coordinate is -1 is right here. So it's this angle that corresponds to this point, which is the coordinates of that point are -1, 0. So obviously the x coordinate is -1 here is what we're looking for, and that angle is pi, or 180 degrees, but I'm just going to put that the answer to this in radians is pi. That's it. All right, let's move on. We are now going to look at number 5. So number 5 wants to figure out what tangent of arctangent of 10 is. Okay, so this is just so that we understand how inverse trig functions work when they are composed with their trig functions. So the normal idea here would be that if you're going to put tan together with arctan, that they should undo one another, and it should just spit out the input and give you 10. And that's true, but not always. And we just have to be careful with a few different things. First of all, we need to know what is the domain of arctan. And the way I can get at this is just going back and reviewing real quick what tangent looks like. So the tangent function looks like this. This is tan x. And so the domain of the tangent function is, well, this is just one period. There's another period over here, another one over here. But the one that we are going to look at is the one between negative pi over 2 and pi over 2. So the domain of this that we're looking at is negative pi over 2 to pi over 2. Now the reason we do that is so that we just get one cut of this graph so that we can define an inverse function on it. So the range is, that should be parentheses, negative infinity to infinity, meaning that the outputs, the y values that come out of this, go from negative infinity to infinity. So that's our domain and range. Now, when we try and graph the inverse tangent function, arctan x, you basically get two horizontal asymptotes, and then your graph is going to look something like, where's my blue here? Graph will look something like this. So the domain of this is everything, and the range, the outputs, are only between negative pi over 2 and pi over 2. So that's this value here, that's pi over 2, and this value down here is negative pi over 2. So you can see that when you look at the tangent function, this is its domain, and then the arctangent function, that's actually the range. That's the connection between these. They swap places, right? That's one of the fundamental ideas behind functions in their inverses, that the domain and ranges swap places. So why is this important? Well, when I'm looking up here at arctan, I need to ask myself, can I plug 10 into this? Okay, can I plug 10 in? Well, arctan, the domain is everything. So this is valid, okay, and it's going to spit out some value, and then that value, when I take tangent of that, it should take it back to 10. So I guess what I'm getting at is there's no domain issues to worry about here, but it's something we should understand is a characteristic of the tangent and arctan together. We don't really have any domain issues. And the key is that the domain of the arctan is everything between negative infinity and infinity. Now I believe on the next one we'll kind of see, this was part A, on the next one we'll kind of see what I mean. Let's look at part B. We're looking at arc sine of 7 pi over 3. Okay, so first of all, the sine function, if we look at sine, we know sine goes like this and goes back. But if we're ever going to define the arc sine function, we have to cut it somewhere. So we cut it between negative pi over 2 and pi over 2. So we come in here and we arbitrarily cut this function right here, and we just look at this piece in here. If we just look at that piece in here, then it makes sense to define an inverse function. And the inverse function will basically have a swapped out domain and range. So here I'll just put domain of this one is negative pi over 2 to pi over 2. And the range on this one is everything between negative 1 and 1. So we get the whole range up here, all the way up to 1, all the way down negative 1. So when we look at the inverse sine function, we're going to have a reverse. The domain is going to go between negative 1 and 1, and the range is going to be out here to pi over 2 up here, and negative pi over 2 here. Okay, so that's just to kind of illustrate how that is similar to what we just did. There's the graph. We don't really need that, but that just give you an idea of what's going on there. Okay, so just remember though, for this picture to work, we have to be dealing with angles between negative pi over 2 and pi over 2. All right, that's the output of this inverse trig function. Okay, so whatever our answer is, we have to take the arc sine of it. Whatever this answer is has to come from in here. So it has to be between negative pi over 2 and pi over 2. All right, so let's go after this problem. So the first thing I'm going to do is just look at this right here. What is sine of 7 pi over 3? So I'm going to go back to my unit circle. And I'm going to start kind of counting my way around here. We have pi over 3's here, 2 pi over 3's here, 3 pi over 3. Let me do this in a different color. I have pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Here's 6 pi over 3. Okay, 6 pi over 3 is the same as 2 pi. And then we get back here to 7 pi over 3. So if we go around and back to here, that is 7 pi over 3. And what we want to know is, what is sine of 7 pi over 3? Well, sine would be the y coordinate of that point, which would be root 3 over 2. Now that's just, again, you have to know that. So here's what I've got. I've got from this up here, I know when I use this tablet I make a mess. I'm sorry, it looks so crappy. So the inside of this, which we just figured out, is actually root 3 over 2. Okay, so now what we do is we say, all right, so let's just kind of start over and make this our problem. This is really saying to me, sine of what angle is equal to root 3 over 2. So it wants me to go look at the unit. Oh boy. Whoa. Where did my stuff go? Wants me to go look at the unit circle. And it wants me to know where the y coordinate is root 3 over 2. However, I am only allowed to look between negative pi over 2 and positive pi over 2. And we already know that that y coordinate is going to happen here. All right, this is 1/2 and this is root 3 over 2. But this angle here, this angle, is not the same as 7 pi over 3. 7 pi over 3, that angle has us going all the way around. See, but you're not allowed to go through that region, so that's no go. That can't do that one. So we got to do the smaller angle in here, and that smaller angle is going to be just pi over 3. So the answer to this is pi over 3. And so back up here to the original problem. Get all this, oops, all this out of here. The answer to this is pi over 3. And so you can see that these two functions, even though they're inverses, they should wipe each other out. In this case, it does not just return 7 pi over 3. That doesn't happen. So you have to actually go through this process of analyzing all of this. You don't necessarily need this and this. What you really need to know is that when you do arc sine, you have to cut off that left-hand side. So that's a big difference from what we just saw in part A. All right, so that's 5A and B. Let's now take a jump here to number 15. All right, so let me look at 15. And I'm actually going to try and pause this real quick. Got to do something. All right, back to this. All right, so number 15. We want to prove that the derivative with respect to x of cosecant inverse of x is equal to -1 over x times root x squared minus 1. All right, so this, I'm sure I did in class one of these, so let me show you the standard setup for this. What we're going to do is we're going to call y is equal to cosecant inverse of x. All right, so we want y prime, or the derivative of y with respect to x, however you want to look at it. Now, to do this, I'm going to first take cosecant on both sides. And the effect of doing cosecant on the right side is that cosecant of arc cosecant of x, that should just give us x, so long as the domain restrictions are satisfied for x. So we're just going to assume that those are. All right, and now we will continue. Now what we do is we take the derivative implicitly on both sides of the equation. So I'm going to take derivative with respect to x on the left side, and then I'm going to take derivative with respect to x on the right side. Now on the right side, the derivative is just 1, so that's all great, no problems there. But the derivative of the right side is a little different because the argument of the trig function y, the derivative of that with respect to x is dy dx, or if you'd like, y prime. Those mean the same things, by the way. Dy dx and y prime generally mean the same thing. So what I'm going to have to use here is a little chain rule. So first I need to know or remember that the derivative of cosecant x, the derivative of this, is negative cosecant x cotangent x. All right? So that would have been from Cal 1. So this is y in here, so the derivative of this is negative cosecant y cotangent y. But now the chain rule says times the derivative of the argument, the derivative of what's inside there, and that is, I'm going to just call it y prime instead of dy dx. So there's our chain rule. Now we're trying to solve for y prime. So what I'm going to do now is I'm going to isolate this one right here. And so I'm just going to move the other stuff to the other side. So when I divide through by this piece here, I'll just put that negative on top. It doesn't matter if you put the negative on the top or the bottom of a fraction. I have cosecant y cotangent y. There we go. So now I have the derivative, but it's in terms of y. See, my derivative has y in it. I'd like for it to have x because the original problem had x in it. So to go back and get that, what I'm going to need to do is draw myself a reference triangle. And I will start out with this information right here. Cosecant of y equals x. So if I call this angle here y, all right, this angle is y, then this equation really means that the reciprocal of sine is equal to x. And I'm going to look at x as being x over 1. So sine is opposite over hypotenuse, and that means that cosecant is hypotenuse over opposite, and therefore my hypotenuse side must be x and my opposite side must be 1. So this triangle, this right triangle here, is a visual representation of this equation, all right? And the importance of that is, in my answer, I need to know what cosecant of y is, and I need to know what cotangent of y is. Now, cosecant of y, I already have that. I know cosecant of y was x. So I already know that this piece here is going to turn into x. The question is, what is cotangent of y going to turn into? So I go back to my triangle here, and cotangent is the reciprocal of tangent. So I actually need to know the opposite and the adjacent side. So I need to solve this side of the right triangle. And that I can do very simply. I just use this idea here, Pythagorean identity. And that just tells me, let's see, we'll call this side A, this side is B, and then this side is like C. So if I just rewrite this equation, it's a squared plus 1 squared equals x squared. And if I solve for a squared, I get x squared minus 1. And if I solve for a, I get square root x squared minus 1. I get plus or minus, however, a is the length of this side, so we will throw out the negative. So a is just root x squared minus 1. Okay, so that's this side, root x squared minus 1. So when we're looking at, what is cotangent of y, cotangent is tangent flipped over, so it's 1 over tangent of y. And remember, tangent is opposite, which would be 1 over adjacent, which would be this root. And so, let's see, root x squared minus 1. So when you have a fraction over a fraction, right? When you have 1 over a fraction, it flips. So this is really just root x squared minus 1. So that's what cotangent of y turns out to be. So the derivative of y is what we wanted. We had it, but it was in terms of y. And now when we write it in terms of x, put the answer up here. When we do it in terms of x, y prime will be equal to negative 1 over, now we had this x right here on the bottom. So we have x, and then we have the cotangent of y, which turns out to be this. So that goes right there. So that is root x squared minus 1. And that matches what we were trying to show. Okay. So that's number 15. All right, where are we at? Number 16. Oh, what happened? Whoa. Okay, 16. Y is equal to arctangent of x squared. And we want to know what the derivative is. So we need to take the derivative of this function. Now just remember, if y equals arctangent of x, the derivative of this is 1 over 1 plus x squared. And that would be it. But we're going to have to deal with some chain rule here because the argument inside is x squared, not x. So the derivative should be 1 over 1 plus the argument, which was x squared, but then squared. So that falls in that pattern that we have over here. But then, because of chain rule, we have to then multiply it times the derivative of what's in there, right here. The derivative of what's in there is 2x. And that's just going to slide up on top. And then on the bottom we get 1 plus, and when we square x squared, we get x to the 4th. So that's what we got there. That's your 16. And 17. All right, 17. We've got y equals arctan of x, but then that quantity squared. So that's the difference. There's a difference between this one and the one before it. On the one before, the squared was affecting just the argument inside the arctangent function. Here the squared is affecting the entire arctangent function. Therefore, when we take the derivative, we have to first start out with a power rule. That 2's got to come out and pop out. Then we rewrite the base like this, and then the power goes down by 1. So that's just power rule. But then chain says now we need to take derivative of what's inside here. And that's just 1 over 1 plus x squared. That's the formula. And so we're kind of here. Let me see. This stuff here can just hop up on top. So 2 arctangent x over 1 plus x squared. And that should do it. All right. Let's take a look at number 18. G of x equals root x squared minus 1 times secant inverse of x. And just as a reminder, the derivative of secant inverse of x would be provided to us on page 183, and the derivative of that is 1 over x times the square root of x squared minus 1. Okay, so just keep that in mind. So what we've got here is a product right here. We've got 2 factors being separated there. And so when we take the derivative here, we're going to need to use the product rule. So we first need to take derivative of this one, then multiply times that, then add to that the derivative of this times this. So hopefully you've done the product rule many, many times. So let's try this. What is the derivative of that piece right here? Well, it's the square root of something, right? And we should have learned in Cal 1, derivative of the square root of something is 1 over 2 times the square root of that something. That hopefully is something that you were shown, just a quick way of doing derivatives of square roots. But then we have to go in and take the derivative of what's inside the root. And what's in there, the derivative of that is just 2x. So that would complete the derivative of that first factor. Now the product rule now says multiply it times the second function, and then add to that, and what is it? Okay, add to that the derivative of the second function, which we wrote down over here, times the first function, which is this one. Ooh, that's nice, because these guys are going to cancel, and these 2's cancel. Let's see what we've got here. We've got up in the numerator of this one, all that's up here, so that gives us x secant inverse of x on top. We've got a root x squared minus 1 underneath it. Then we still have over here the plus sign. And then over here, this was just 1 over x. And that's fine with me. I mean, we could get a common denominator, but I don't even see the reason why. Just leave it like that. There's our derivative. Okay, let's see if we can't squeeze 19 in here. Y equals arc sine of 2x plus 1. So remembering what the derivative of arc sine of x is, 1 over square root 1 minus x squared. And again, that would also be on page 183 if you needed to check with that. That's our general formula. However, here the argument is x, here the argument is 2x plus 1, so we'll have some chain rule to deal with here. So the derivative would be 1 over the square root of 1 minus, and then 2x plus 1, that's the argument, squared, then times the derivative of the argument, which would be 2. So we'd be looking at 2 over square root of 1 minus, now do we really want to expand that? I guess we could. That would be 4x squared plus 4x plus 1. So that's what happens if we take this and square it. And then we could distribute that negative through. So 2 over the square root, and the negative is going to go here, here, and here, and then this becomes a negative 1 and kills off that one. So all we're going to have is negative 4x squared minus 4x. There we go. That is our derivative. 20. Y is arctangent of x minus root 1 plus x squared. Wow, this is going to be a mess. Okay, so we've got to take the derivative of this, and we have an arctangent. We're going to take derivative of arctangent, but look at that. Look at the argument of that. It's going to be completely nasty. So it's going to be 1 over 1 plus the argument squared times the derivative of this. Now when I take derivative of this, I'm going to get 2 terms, so I have to take derivatives separately. And that means I need a parenthesis here so I can do derivative of each one. So derivative of x is 1, so that piece is gone. Minus, now derivative of the root of something is 1 over 2 times the root of that something. Then times the derivative of what's underneath that root, and that is 2x. Alright, this looks bad. 1 over 1 plus x minus root 1 plus x squared times, and then over here the 2's cancel, so 1 minus x over root 1 plus x squared, like that. Okay, and I guess we could take this whole thing and just put it up on top here, and you could probably even expand this out or somehow get common denominators, but I am going to just leave it just like this and box it. I mean, this is the derivative. The book may go further than that, but I'll leave that to you to try and figure that out algebraically. It's going to take me too long. Okay, 21, capital G of x. I should say that if you have a question on that, you should come by and ask me if you can't simplify it, because that is a crucial skill, is to be able to simplify that. but it's just algebra at that point. Okay, so we've got this, and I changed it. They used arc cosine. I just put the cosine with the -1 up there. So this we need derivative of, and we've got a little product here. So the derivative will be the derivative of that root function first. We've got to go times the derivative of what's under here, then times the second factor, or the second function here. Then plus, now the derivative of arc cosine, again, can be found on page 183. And it's very similar to the derivative of arc sine. It's just got a negative in front of it instead. So negative 1 over square root of 1 minus x squared. So that's your derivative of this. And now you need times this one. Square root of 1 minus x squared. And look at that, these cancel. Great. And so it should just be, let's see, I got some 2's cancel here too. So I should just have a negative x arc cosine of x on top. Should have a root 1 minus x squared down here, and then plus, oh no, I can change that to a minus 1. So that takes care of this piece right here. And that's it. Again, you can get a common denominator there, but it's good enough. 22. To capital F of theta equals arc sine of the square root, I'm putting in parentheses, the square root of sine theta. Ooh, this looks messy. All right, well, this is the argument of an arc sine function that we're taking the derivative of. So the derivative of this will be the derivative arc sine of something, which is 1 over the square root of 1 minus whatever this argument is squared. So when I take that root and square it, I just get 1 minus sine theta. That's nice. The root went away. Then times, now I need to, I've done the derivative of the arc sine. I need to take derivative of the rest of this. And now I have this root to take care of. So what is the derivative of the root of something? 1 over 2 roots of that something. So I've taken care of the root. Now go inside that, take derivative of sine, that's cosine. And so that's it. I could put all this together, put cosine theta on top. On the bottom I could just have root 1 minus sine theta, and then times, oh, let me put the 2 out here, times root sine theta. Something like that. You could combine those two roots together if you wanted to. If you did, it would look something like this. 2, you would have a single root, and then basically this and this multiply, so that sine would have to distribute through, and it would become something like that. So it's like the sine goes here and here. All right, that's good. 23. H of t equals cotangent inverse of t plus cotangent inverse of 1 over t. Remember, 1 over t is the same as t to the negative 1. And the reason I say that is because we're going to need its derivative in a little while. And when we take derivative, it's negative t to the negative 2. So power rule drops out, right? Subtract 1. This is really just negative 1 over t squared. Okay, so hopefully you already know how to get from here to here because you did it so much in Cal 1. All right, so here we go. We need to know what the derivative of arc cotangent of t is. And I'll put that over here. The derivative of arc cotangent of x, according to the formula, is negative 1 over 1 plus x squared. Okay, so the derivative of h with respect to t will be, well, this is like basically saying the derivative of arc cotangent of x, except it's t. So it's just going to be, there we go, that's it. And then we say plus. Now the difference here is that we're going to do negative 1 over 1 plus, but we're going to be squaring this instead. So it's going to be 1 over t, and when you square it, you square the top and bottom, so you're just going to get 1 squared, which is 1, over t squared, which is t squared. But then you have to multiply by this, right? That was the derivative of 1 over t, so we have negative 1 over t squared here. And this looks a little messy, but I'm going to do this multiplication here. I'll leave this first one alone. And notice what happens here. Negative and negative become positive, so we have positive 1 on top. And then this is 2 terms, and we're going to multiply the bottom, so it's going to go through here and here. And when you do that, you get t squared plus 1. Because, you know, this times 1 is just t squared, and then when you do this times this, you get t squared over t squared, which is 1. And check these things out. These are the same thing. They're just opposite in signs. So they add up to be 0. So derivative of that function is always 0. Interesting. Mean slope of the tangent line is flat everywhere. Everywhere it's defined, I should say. All right, 24. 24. Y is cosine inverse of sine inverse of t. Ew, yuck. So y prime, okay, derivative of arc cosine of something is negative 1 over the square root of 1 minus the argument, whatever was in it, arc sine of t squared. As bad as that looks, that's what it is. Times, now we've done that, let's take derivative of arc sine of t. Derivative of arc sine of t is just 1 over the square root of 1 minus t squared. And that's it. I don't think I want to touch that. Not much you could do with that. 25. Y is equal to arctangent, which I'm going to write this way, of cosine theta. So the derivative of this, well, derivative of arctangent of something is 1 over 1 plus whatever that something is, squared. So I'm going to square that cosine. Then times derivative of cosine, which is negative sine. So we've got negative sine theta over 1 plus cosine squared theta. Be careful. If that was 1 minus cosine squared theta, we could do something, but it's not. It's 1 plus cosine squared theta, so we'll just leave it. 26. F of x equals x natural log arctangent of x. All right, so we have a product rule here. Be careful. There's your product. So when we take our derivative here, it's going to be derivative of this one, which is 1, times the second one, natural log of arctangent of x, then plus the derivative of the second one. Now, the derivative of natural log of something is 1 over whatever that something is. So arctangent of x. Times, chain rule, the derivative of what was inside the natural log. So derivative of arctangent of x is 1 over 1 plus x squared. And then finishing off the product rule times this x here. So, yuck. Natural log, tangent inverse x. Plus, let's see what's on top. The only thing on top there is that x. So x over, and then I can put arctangent x, and then I can put in parentheses 1 plus x squared. And that's about it. I will leave it. All right, 27. I'm going to take a quick break here. Excuse me. I had to get something to eat. Working on 27. This one looks pretty weird. I think some good things are about to happen though. Okay, so we do have a product rule happening here, but this guy over here is separated by addition. So I can just take the derivative of this. No big issues here. So that's a derivative of the root of something, and then derivative of what's inside. Okay, and that'll be the derivative of that. Now over here, I've got to do a product rule. So derivative of the first one is 1 times the second one, plus derivative of arc sine of x is 1 over root 1 minus x squared times this first function, which is just x. And then we still have all this plus that. Okay, these twos cancel. And so we've got arc sine of x plus x over root 1 minus x squared. And then over here we still have that minus sign, so we're going to have minus, and we still have that x. So we got minus x over root 1 minus x squared. And check it out, these go away. So your answer is arc sine of x. Huh. All that. This nasty thing, when you take its derivative, you get arc sine of x. Interesting. Excuse my chewing here. Y equals arctangent of root 1 minus x over 1 plus x. Man, this looks like it's going to be a mess. All right, let's do it. Y prime equals. So I need to take derivative of arctangent of something, right? The derivative of that is 1 over 1 plus whatever this something is squared, and that's great because it'll just kill off that root. And that's what I've got. Okay, so that takes care of just the arctan part. Now I got to go and take a look at this root part, right? The root part is the next part of the chain rule. So the derivative of the square root of something is 1 over, oops, I don't need it to be that big, 1 over 2 square roots of that something. And that something is 1 minus x over 1 plus x. Okay, so I'm done with that. Now I need to go in here and take derivative of this. And that is a quotient rule. So I've got to do over here, it's that good old like f prime g, minus g prime f all over g squared. So however you learned it, I've got to do that here, quotient rule. So I take derivative of this first, the top, the whole top. Derivative, that's -1, times the bottom, minus the derivative of the bottom, derivative of the bottom is 1, times the top was 1 minus x, all over the bottom squared. Okay, let's see what happens here. We get -1 minus x minus 1 plus x. The x's here dial off. Just get -2 on top there. All right. Wow, lots of things I can do here. Which is kind of right where we are here. Keep grabbing the wrong pen here. 1 over 1 plus 1 minus x over 1 plus x times, I'm just trying to think of how I want to do this. Let me do it this way. Root 1 plus x over 2 root 1 minus x. So all I did there was I used a property that if you have a fraction under a root, you can really just take it and break it up into 2 roots. And then since this is 1 over a fraction, it just flips over. So this basically comes up here and this one stays downstairs. So that's what I've got happening here. And then I have times, this was -2 over 1 plus x, that quantity squared. I do get another cancellation here. This 2 and this 2 go away. So I still have a -1 here. And let me see what else I can do here. I mean, I could stop now, but I'm going to keep going. So check this out. In the denominator here, I'm going to get a common denominator. So just keep in mind that's really over 1. So I need to introduce a 1 plus x here and a 1 plus x here. And what would that give me if I put this all together? I'd have the 1 on top up there. I would have 1 plus x plus 1 minus x over the common denominator, 1 plus x. times this over here. Oh, too bad those don't cancel. 1 minus x. And then over here, negative 1 over 1 plus x squared. All right. Now, these x's cancel. I should just get a 2 there. So watch this. 1 plus x over 2. So again, because this up here becomes a 2, and 1 over a fraction flips, I just get this thing right here. Okay, and then I have root 1 plus x over root 1 minus x, then times negative 1 over 1 plus x squared. Okay, now check this out. Just keep in mind that this right here, this one, and erase that root, that's the same as raising it to the 1/2. And notice that these two are the same thing, right? Except this one is like raising it to the 1. So what I can do is I can put these two together with multiplication. That means you add the exponents. So I should have, I'm actually going to incorporate this negative in here also. I should have a negative, then I should have a 1 plus x, and when I add 1 and a half together, I get 3 halves. And then over, on the bottom I have that 2, I have that root 1 minus x, and I also have a 1 plus x to the second power. And now, take a look, these are the same also. So here's where I will subtract exponents, right? When I'm putting these two together, I'm basically going to have 1 plus x to the 3 halves minus 2, which should be 1 plus x to the negative 1/2. And that really means that that root belongs on the bottom. So we should have negative 1 on top. We should have 2, we should have root 1 minus x, and then we also have a root 1 plus x down here. That comes from this idea right there. And you could even put these two roots together now, and you can multiply their insides together. Negative 1 over 2, and when I multiply these two insides together, oops, I'm doing 1 minus x times 1 plus x. That's difference of squares, and that should go back to be 1 minus x squared. Yikes. That's it though. All right, that's number 28. What else we got? Number 32. A couple more to go here. 32. Okay, so it says here, find y prime if tangent. Okay, so they give you that tangent inverse of xy equals 1 plus x squared y. So we're trying to find y prime. So we're going to have to use implicit differentiation because we've got y's and x's in a way that we can't separate them and solve for y. So I'm going to do it implicitly. I take derivative on both sides with respect to x. So when I take derivative on this side with respect to x, I get 1 over 1 plus the argument xy squared times the derivative of the argument. Now let's pay attention to this. This is the argument. That has a product. I must do the product rule there. Derivative of x is 1 times y, plus derivative of y is not 1, it's y prime, and then times x. Okay, so that's a very important part right there. And then we can continue, and we say equals. Now derivative of the right side, well, derivative of 1 is 0, so I don't care about that. Plus, now over here we still have a product rule right there. So we got to do another product rule here. I'll do it in red. So derivative of x squared is 2x times y, and plus derivative of the second function y times the x squared. And that's all good, but now we need to solve for y prime. So we need to look and try and get all our y primes together on one side of the equation. Problem is, it's trapped in this parentheses. So I have to actually distribute this nasty thing through to both of those. Well, that looks bad, but it's actually not that bad. So this is really y. So that's y over 1 plus, I'm going to write as x squared y squared. Okay, so that was distributing this through to that. That numerator, that y just joined on the numerator. And then I'm going to go here to here. That's going to say plus, let's see, y prime x goes on top, and then I still have that same denominator. And then on the right side, I still have 2xy plus y prime x squared. Okay, now, let's try and get our y primes together on one side. So I'm going to leave this one here. move this one over, which is going to make it negative, and then I'm going to take this here and move that to the other side. So I should have y prime x over 1 plus x squared y squared minus y prime x squared equals 2xy minus y over 1 plus x squared y squared. All right, the whole idea behind that is to be able to now factor a y prime out on the left-hand side. Pull a y prime out. I'll be left with the x over 1 plus x squared y squared. And when I pull the y prime out of the second term, I get just x squared. So I just pulled this y out, the y prime, sorry, out, equals 2xy minus y over 1 plus x squared y squared. So now what I'll do is I will just basically take this side, divide it by all of this, and this side divided by the same thing. So we're going to just clear everything out so that we have just the y prime on the left. So we get y prime on the left. On the right we get 2xy minus y prime over 1 plus x squared y squared over x over 1 plus x squared y squared minus x squared. So that was this piece right here. Just divide it, I put it underneath there, and that's what we've got. I'm sure the book doesn't have that as an answer. What they're probably going to do is try and clear these fractions out. So they're going to multiply the top and the bottom by 1 plus x squared y squared. And that will have the effect of eliminating some of those fractions. For example, I go here to here first. It gives me 2xy times 1 plus x squared y squared. Then when I go here to here, the numerator and denominator cancel. All you're left with is that y up there, which is great. And then when I do this one here, same thing happens. All I'm left with is that x. And then when I go here to here, I'm going to have minus x squared, and then in parentheses 1 plus x squared y squared. And then you can distribute this through. So let's see where that takes us. We'll have 2xy, that's distributing to the 1, and then we'll have plus 2, what's that, x cubed, y cubed? And we still have minus y. All over, and on the bottom, we'll leave this x here, distribute this x squared through, so minus x squared, minus again, x to the 4th, y squared. Gosh, that looks pretty bad, but hey, there we go. There's our derivative. That is y prime. All right, what else we got here? Supposed to do 32 and 39. Okay, yeah, so this is Cal 2. We can do this one. All right, so number 39, you don't have to read the whole thing, but it basically says you got a 10-foot ladder leaning against a wall. So here's a wall, got a ladder. Ladder's 10 feet. The bottom of the ladder slides away from the base of the wall at 2 feet per second. So this point is moving this way at 2 feet per second. How fast is the angle between the ladder and the wall changing? So we'll call this angle theta here. So they want to know how fast that angle is changing exactly at the moment that the ladder is 6 feet from the base of the wall. So things are moving in this picture. This is moving down, that's moving over. This angle is changing, right, over, as time goes on. So this really depends on how you learned how to do these in Cal 1. These are related rate problems. I always tell my students to draw a general picture, which is what I have here. General picture, the variables are in motion, everything's moving. And then you have a picture of what's happening at the instant in question. And at the instant in question, our ladder is actually in this position. It's a 10-foot ladder, and this side from here to here is 6 feet. So 10 feet here, 6 feet here. That's the instant in question. And what we want to know is what is d theta dt? How fast is theta changing with respect to time? We're given the rate at which this point right here moves. So I'm going to call the distance from here to here x, and we know that dx dt, the rate at which x is increasing, is 2 feet per second. and we want to know something about theta. All right, so we want d theta dt. We want this, let me get back to what we want. We want this at exactly the moment x is 6, right? Okay, so now once we kind of set this part up, what we want to do is come up with an equation. Something that's going to have theta in it and have x in it. So we have a nice right triangle here. And what we can do is we can use a trig function like sine. Sine of theta would be the opposite side, which is x, over 10, which is the hypotenuse. So that would be a legitimate equation to use for this problem. And in Cal 1, you could have done this. You could have just taken the derivative implicitly with respect to time, and that would be it. But this is a section on inverse trig functions. So what I'm going to do here is I'm going to take arc sine on both sides. And let's see how this might make this easier. Arc sine of the right side. So we take arc sine on both sides before we do any derivatives. And we get theta equals arc sine of x over 10. So check this out. If I take the derivative now, okay, I come in here and I take the derivative with respect to t here, and derivative with respect to t here, I get d theta dt on the left side equals, and see, that's great, okay? It's great that d theta dt is here because that's exactly what I want to know. I don't have to solve for it, it's right there. And then on the right hand side, I need to know what the derivative arc sine of something is, so it's 1 over square root of 1 minus the argument squared, so x squared over 100. And then times the derivative of what's in here, and just remember that's the same as 1/10 x, so derivative of that is 1/10. But remember, the derivative of x is not just 1, it's dx dt, because it's with respect to time. So now all I'll have to do to figure out what d theta dt is just plug in the things I know. See, I know x, it's 6 in this problem, and I know dx dt is 2. So this just becomes 1 over the square root of 1 minus 6 squared is 36 over 100 times 1/10 times dx dt, which was 2. And you could just figure out what this is some decimal answer, and it will give you the rate at which the angle is changing. And just be aware that that answer will be in radians per second. Okay? I'm not going to do it. I don't have a calculator with me, but that should do it to help you get through that problem. And that does it for this section.